Welcome back to Very Ordinary Differential Equations. In this video, we move on to the study of linear first-order inhomogeneous equations. So we are now interested in solving the inhomogeneous or non-homogeneous first-order linear differential equation, y prime plus a function of x times y equals some other function of x. Now this function on the right is no longer going to be constantly zero, but suppose that you can solve the complementary homogeneous equation. You have found a function, and we're going to call it y subscript 1, which solves this equation right here. So having started with this inhomogeneous first order equation, if we replace this what's called forcing function on the right with 0 and turn it into a homogeneous equation, we know how to solve that. We did it in the previous video. So let's presume we've already done that work and we have found a single solution, y sub 1, to the homogeneous equation, which is called the complementary equation. Now we're going to presume that the function y that solves the linear equation at the top is some unknown function of x u of x times the function we already found, y sub 1. So y sub 1 solves the complementary homogeneous equation, and u is an unknown function, and we're crossing our fingers and hoping that u of x times y1 happens to solve the inhomogeneous equation. Well, if we were to take a derivative of u times y1, right, y is u times y1, so if I take a derivative of this, I apply the product rule, and here it is, u y1 prime plus u prime y1. We take this for y prime and put it back up here for y prime, and we're going to take u sub y1 and plug it in for y and see what happens. Well, we end up with y prime plus p of x times y equals f of x, and we've made those relevant substitutions. And here's where we are so far. Y sub 1 solves the complementary homogeneous equation, and we're hoping that u times y1 happens to solve the equation we began with. And under the assumption that it does, we ended up here. Now notice there are two terms, the first and the third, from which I can factor out a u. Now what's left behind when I factor a u out of this first term and this third one is y1 prime plus p of x times y1. But y1 was taken to be a solution to the complementary homogeneous equation, meaning y1 prime plus p of x times y1 is always 0. So that parenthetical term must always be 0 under the assumption that y sub 1 solved the complementary homogeneous differential equation. And then we can get rid of it. We can now solve this for u prime. U prime must be f of x over y1, and maybe we can anti-differentiate that. So if we can solve that u is an antiderivative of f of x over y1, in that case, y equals u times y1 will be a solution to the original equation. There was the original equation there. So we've broken down the process into first solve the complementary homogeneous equation and then try to do this integration here. And if you can do that as well, then u times y1 will be a solution to the equation you began with. This technique is called the variation of parameters. When we solve for u, a constant of integration will be introduced. Specifically, having solved for u to be an antiderivative of f of x over y1, I really do need to add a plus c in there. And the constant of integration is going to be what generates our family of solutions. Okay, so u plus any constant times y1 will be a solution to the original equation. And if I distribute this out, we get u times y1 plus an arbitrary constant times y1. Now this arbitrary constant times y1 describes the entire family of solutions of the complementary homogeneous equation. So if y1 is any solution to the complementary homogeneous equation, and u is any antiderivative at all of f of x over y1, then all solutions to the original inhomogeneous equation will be given by exactly uy1 plus a constant times y1. So if all solutions are given by uy1 plus a constant times y1, well, what does that really tell us? y1 was any solution to the complementary homogeneous equation, so that term, as mentioned, cy1, is the full family of solutions to the complementary equation. The one particular u we found yields one particular solution to the inhomogeneous equation. And then u times y1 is often denoted as y sub p for a particular solution to the inhomogeneous equation. So all solutions are now given by the one particular solution to the inhomogeneous equation we found, plus the entire family of solutions to the homogeneous differential equation. So to briefly summarize, we want to find all solutions to y prime plus p of xy equals f of x. First, what you do is find a single solution to the complementary homogeneous equation where you replace f of x with 0. If you can find a single solution to that, call it y sub 1. Next, find a single solution u to an antiderivative of f of x over y1. You can make any choice you want for the constant of integration. 9 times out of 10, 0 is going to be your best bet, but if the particular form that you're working with means another constant would be more convenient, by all means, pick any constant you want. In which case, y sub p is u times y1 is one particular solution to the inhomogeneous equation, and then all solutions to the inhomogeneous equation will be given by the family y sub p plus a constant times y1. Now let's put all of that theory into practice by finding all solutions to y prime plus the sine of x times y equals x times e to the cosine of x. The first thing we need to do is find a solution to the complementary equation, where we replace this forcing function on the right with a 0. So y prime plus the sine of x times y equals 0. We can do this using techniques from the previous video. This is now a linear first-order homogeneous equation. And if we go through all of that, we will find a single solution of e to the cosine of x. It's just e to a negative antiderivative of that coefficient sine of x. Okay, so e to the cosine of x happens to be one solution to this complementary equation. Now what we do is we solve for one particular solution to the inhomogeneous equation, y sub p equals u times y1, by solving for u is an antiderivative of the forcing function x e to the cosine of x divided by y sub 1 e to the cosine of x. So this e to the cosine of x looked like a very scary part, but it now cancels out. U just has to be an antiderivative of x, and the most straightforward is just x squared over 2. And you can choose any constant of integration you want. If you wanted to call this x squared over 2 plus 17, it would work perfectly well, but why not just use 0 to write less? Having found one particular solution of the form u x squared over 2 times y1 e to the cosine of x, all solutions are given by that right there, x squared over 2 times e to the cosine of x, plus an arbitrary constant times the single solution to the complementary equation we found earlier, e to the cosine of x. So all solutions to the equation we started with, y prime plus the sine of x times y equals x times e to the cosine of x, must be of the form x squared times e to the cosine of x over 2 plus an arbitrary constant times e to the cosine of x. Next up, let's try to solve xy prime plus 4y equals 3x squared with the initial value that y of 1 is equal to 1. We don't quite have this equation in our standard format. We're going to have to divide by that leading coefficient of x. That gets us y prime plus 4 over x times y equals 3x. The complementary homogeneous equation is given by setting that forcing function on the right to be 0. So just y prime plus 4 over x times y equals 0. Now we can solve this as y1 is e to the negative antiderivative of 4 over x. Of course, anti-differentiating 4 over x is pretty straightforward. It's 4 log x. Now we've got a combination of e's and logs. Unsurprisingly, this is going to work out to be x to the minus 4th. You can now check, if you really wanted, that x to the minus 4th as our function y happens to solve the complementary homogeneous equation. We're not necessarily interested at this point in finding all solutions, we just need one. Y sub 1 is x to the minus 4th is a single solution to the complementary equation. So we found that solution to the complementary equation, and now we move on to finding one particular solution to the inhomogeneous equation we began with by solving for this unknown function u. Now u has to be an antiderivative of f of x over y1. The forcing function f of x is 3x squared. The single solution to the complementary equation y1 was x to the minus 4th. And now we have u must be an antiderivative of 3x to the 6th, which is not very difficult to find, 3/7 x to the 7th. Therefore, a particular solution to the inhomogeneous equation is simply this new function u that we found times our original function y sub 1. We've got a 3/7 and we have an x to the 7th times x to the minus 4th. That simplifies as just x cubed. We could have chosen any constant of integration we wanted in u, but 0 is usually going to be the easiest one. Now that we have found a single particular solution to the inhomogeneous equation, all possible solutions must be given by that particular solution, 3/7 x cubed, times an arbitrary constant times the solution to the complementary homogeneous equation, x to the minus 4th. So we now know that all possible solutions to our differential equation are of this form. Y must be 3/7 times x cubed plus an arbitrary constant times x to the minus 4th. At this point, it's time to use our information that y of 1 is equal to 1. Plugging in x equals 1 and setting y equal to 1, we can now solve for c. 1 must be equal to 3/7 times 1 plus c times 1. This gives us that c is 4/7, and now we go back and say the unique solution to the initial value problem we began with is 3/7 x cubed plus 4/7 times x to the minus 4th. This is the only solution to the problem we began with. And now, let's find the general solution, in other words, all possible solutions, to 1 plus xy prime plus 2y equals the sine of x over 1 plus x. So we begin by converting to standard form by dividing out that leading coefficient of 1 plus x. We obtain y prime plus 2 over 1 plus x times y equals the sine of x over 1 plus x squared. Now that forcing function of sine x over 1 plus x squared looks pretty awful. Thankfully, we start solving by throwing it away and solving the complementary equation anyway. And as we've gotten used to by now, solving the complementary equation involves integrating that coefficient 2 over 1 plus x with a minus sign out in front. Okay, so we have negative 2 times the log of 1 plus x. And we have to exponentiate that to get our single solution to the homogeneous equation. So y1 works out to be 1 over 1 plus x squared. Again, a combination of exponentials and logs simplifies things nicely. So a single solution to the complementary equation is given by 1 over 1 plus x squared. So we found that single solution to the complementary equation, and now we have to move on to finding a particular solution to the original inhomogeneous equation. What we have to do is solve for u by integrating f of x over y1. Now f of x is not, as written up here, sine x over 1 plus x. Remember, what we had to do was divide out this coefficient of 1 plus x. So the actual forcing function in the format that we know how to work with is actually sine x over 1 plus x squared, which works out to be really nice, because now when we divide this known solution of y1, the 1 plus x squareds completely cancel, and all we have to do is integrate the sine of x. Well, that's just minus cosine of x plus an arbitrary constant, which we are going to take to be 0. Which means we've actually found a single particular solution to the inhomogeneous differential equation. Having found u equals minus cos x, our particular solution is just u times y1. So negative cos x over 1 plus x squared is one particular solution to the original inhomogeneous differential equation as given here. So if we have found a particular solution to the inhomogeneous equation and can describe the entire family of solutions to the complementary homogeneous equation, well then, all possible solutions are given by y sub p plus a constant times y1. In other words, negative cos x over 1 plus x squared plus an arbitrary constant times 1 over 1 plus x squared. And we just simplify this a little bit, collecting terms to call it c minus the cosine of x over 1 plus x squared. And there we have it. That's all possible solutions to the differential equation as given at the beginning. So what have we done? We're trying to find all possible solutions to a differential equation of a very specific form. Y prime plus p of x times y equals f of x. Notice that the coefficient of y prime is just 1. Also, the function f of x is referred to as the forcing function. The first step is to find a single solution to the complementary homogeneous equation, which you get by replacing the forcing function with 0. Next, you solve for u an antiderivative of f of x over y1, where y1 is the single solution to the complementary equation you found before. You're free to choose any constant of integration you want at this step. You're probably going to pick 0. The family of all solutions is now given by y sub p plus a constant times y1, where y sub p is the u that you found up here, times the y1 that you found at the beginning.